Welcome to the first part of Unit 7. In this unit, we're going to be continuing our investigation of forces by studying Newton's third law. To begin with, we're going to watch a YouTube video. I've already pulled it up, so let me bring it in here. This is the upper of those two links. Both of them are similar. What we have in this video is two giant steam train locomotives that are going to collide into each other. So here we go. It's always got to be dramatic. What can I say? So here comes one train locomotive. Off jumps the engineer. And heading at him the other direction is the other one. And what do you notice? Both trains are damaged, quite damaged in a couple of places. Right? So when they collided together, both trains experienced a force. And this is true for any two things that collide. Both of them experience a force. Okay. Which brings us to, I'm going to pause this and get it out of the way. Move him out of the way. Which brings us to Newton's third law. Newton's third law states that whenever one object exerts a force on a second object, the second object exerts a force that's equal in magnitude but opposite in direction to the first force. The everyday common language version of this is for every action there's an equal and opposite reaction. Personally, I don't like that version of this law. And the reason for it is because when I think of action and reaction, I think of something that happens and then something else that happens as a consequence. So there's a temporal separation between the two. That's not the case between Newton's third law. If one force exists, the other one automatically exerts, the other force automatically exists as well. And I also don't know for some forces how you decide which one's the action and which one's the reaction. Again, they happen simultaneously. Take it for what it is. So reviewing really quick, we now have all three of Newton's laws for forces. So we have the first law, which is an object in motion will stay in motion with constant, possibly zero velocity, unless acted on by a net external force. Newton's second law tells us that if there is a net force, then it equals its mass multiplied by its acceleration. And third law, we just saw, is that when one object exerts a force on a second, the second object exerts a force equal in magnitude, but opposite direction to the first. So now we're going to focus our energies on third law. And particularly, how do we identify these two forces that happen simultaneously? Those forces are called third law force pairs. So here are some things to help you identify them. Okay, they must be equal in magnitude. I think of the things that help you identify them, that is the least useful of them because you can't always tell magnitude right away. Direction you can get just fine. They have to be in opposite directions. They must result from the interaction of two objects. Okay, and they must be between the interactions of those same two objects. And because there's two objects involved and there's two forces involved, those two forces have to be on separate free body diagrams. Okay. If you remember last week, I identified a naming scheme for forces. So remember, I had the force from A on B. So the force caused by A acting on B. If you follow my naming scheme, then the third law force pair is very easy to identify because it's got exactly the opposite subscripts. So the force from A on B is the third law force pair to force from B on A, right? They're resulting from one interaction. A and B are interacting. One force is on each object. They would be on the separate free body diagrams. One would be on B, one would be on A. And if you think about it, so pretend that object A is your friend and object B is you, and you're on ice skates and you push off of each other. That would be the FAB and the FBA, and it sends you in opposite directions, indicating that those forces were in opposite directions. Right? So think about the subscripts. Okay? So let's do an example. So here we have two blocks. For reference, on my computer, this one looks green, so I'm going to call it green. I've had students in the past tell me it's yellow. I don't know as I believe them. Okay, let's first look at the green block and think about the free body diagram there. We have a normal force from the red block on the green block, holding the green block up, and we have the weight from the earth on the green block. And those are the only two forces on the green block. Okay. If we look at the red block, so I'm going to put a big G in here so that we know that that's the green one. And now I'm going to look at the red block. Okay, some forces are easy to find. We know the earth acts on the red block, giving it a weight. We can see that it's on some sort of surface, so that's got to give me a normal force. And then lastly, we've got the green block sitting on top. Well, that green block is going to push down on the red one. So here we have the normal from the green block on the red block. And look at this one versus that one. Two separate free body diagrams. One interaction, red on green, green on red. They are opposite in direction. This one and that one are a third law force pair. Okay. So now, I made this statement back when we were watching the train video that these forces always occur in pairs, and they always have both objects experience a force, those sorts of things. So now let's talk about this. So here we have Sir Speedy colliding with a Mack truck. And if you think about a Mack truck, we're talking about something big, something steel, something fairly unbendable. I mean, it's possible, but it takes a lot of effort. Sir Speedy, on the other hand, is probably in something with a nice fiberglass shell, which will shatter upon impact. And Sir Speedy is not the brightest person in the world here, and he decides he wants to play a nice game of chicken with the Mack truck. Now, remember, a game of chicken involves two people driving in the same direction or opposite directions at each other, and the question is who flinches first and moves out of the way. Well, I mean, the Mack truck, does it really care? Probably not. Sir Speedy, well, as I said, he's not the brightest object in the box here, or sharpest crayon in the box, however you say it. So they collide. And now let's think about the forces on the Mack truck and Sir Speedy during that collision. So we have a normal from the road on the truck. We have the weight from the earth on the truck. There might be some friction, but we're looking over a very, very small instance, so that friction's not going to have a large amount of time to act. On the other hand, we will have a normal force from Sir Speedy on the truck. So this is the truck's free body diagram. So now if I look at Sir Speedy, I have the normal from the road on him, weight of his weight, and then I have the normal from the truck on him during the collision. And again, if I look, there's my two third law force pairs. So this force and that force have to be equal in magnitude. Now, if I think about Sir Speedy, Newton's second law tells me that F net has to equal ma, and vertically these two forces are going to cancel because ideally he's not flying off the road or sinking into the road. So no acceleration in the vertical direction. Therefore, the only force contributing to the net force is the normal from the truck. And that equals Sir Speedy's mass multiplied by his acceleration. And I'm going to take and subscript this for Sir Speedy's acceleration, so we know it's different. If, on the other hand, I look at the Mack truck, well, his mass is going to be much bigger, so I'm going to draw it bigger so we got it there. And then we have his acceleration. And again, this truck isn't flying off the road. It's not sinking into the road. There's no vertical acceleration. So the only force causing the truck to accelerate is, again, the normal force that results from him crashing into Sir Speedy. That's his mass multiplied by his acceleration. Now look. I'm going to change colors to illustrate here for you. This side and that side are third law force pair. Therefore, those are equal in magnitude. Yes, they're equal in are opposite in direction. That's going to result in the accelerations being opposite in direction. Not worried about that in this case. But if this side and that side are equal, and Sir Speedy's mass is less than the mass of the Mack truck, that means Sir Speedy's acceleration must be larger. Okay, so now I'm going to write that out in long form. Because NST equals NTS by third law. And because little m is less than big M, that means that Sir Speedy's acceleration has to be greater than the Mack truck's acceleration. Okay? The acceleration Sir Speedy experiences is bigger than the acceleration that the truck experiences. And the question now is, can Sir Speedy's structure withstand an acceleration of that size? You know, probably not if he's made of fiberglass. Okay. This is even more magnified or exemplified if you think about, instead of this being Sir Speedy, think about this being your favorite bug hitting the windshield of the truck. The forces are equal, but the bug experiences a much, much larger acceleration, and therefore the effect is very different on him. Okay, so now remember what third law says. The third law says that we have forces that are equal in magnitude and opposite in direction. So let me set up this example. Here we have a cup sitting on a table, and I'm going to look at the free body diagram of that cup. So we have a normal from the table on the cup, and we have the weight of the the cup being going downward. And now let's think about these two. Is the cup accelerating upward off the table? Well, not presently. I mean, there's nobody sitting at the table to cause it to accelerate. Is it falling through the table? Well, it wouldn't be much of a table if it was falling through the table. Therefore, I argue that this cup is stationary. And it's going to remain stationary because it's stationary, and more importantly, because it's going to remain stationary, these two forces are equal. So the normal force from the table on the cup has to equal the cup's weight in these circumstances. So here I have two forces, a normal force and a weight force, that are equal in magnitude and opposite in direction. So they seem to meet the criteria for third law. But these are not, let me repeat, these are not a third law force pair. And the reason for that is this statement right here. The reason that they are equal is because it's not accelerating. So the reason they're equal is an argument that comes from Newton's second law. Because the acceleration is 0, I can say the net force is 0. And then if I plug in my other two forces, so the normal from the cup, table on the cup has to equal the cup's weight. And that statement will only be true as long as the acceleration is true. I mean, it's kind of hokey, but, you know, in maybe a posh hotel somewhere, you have a table in the elevator and you can sit down at the table in the elevator and ride the elevator up to your floor. I know, I'm stretching it a little bit here. But as we saw last week with the elevator example, when the elevator was accelerating, the normal force in that example did not equal the object's weight. And the same would be true here. Okay, so these are not a third law force pair. So let's write down the reasons that they're not third law force pairs. Things that you could answer, for example, on a quiz. So not third law because one possible solution. They're only equal, I'm going to use because A equals 0. So B/C means because. Hopefully you're familiar with that. Other things you could pay attention to. We're only dealing with one object. And remember, third law force pairs requires the interaction of two objects. We're only looking at the cup. We're only looking at the cup. So we've only got one object. We've also got two types of interaction. Two types of interaction? Well, one of these interactions is a contact force, the normal force. The other one is a non-contact force, the cup's weight. For a third law force pair, you must result from one interaction between two objects. So we have two different types of interactions here. Okay. Things you could look at. It's not the same two objects, right? We don't have the flipped subscripts, if you will. So we can put that down here. The flipped subscripts are not present, right? It's not normal from the table on the cup and normal from the cup on the table. It's normal in weight. One's between the table and the cup, one's between the earth and the cup. So there are 4 good reasons that these are not a third law force pair. Okay, so now let's move onward. And again, look at our green block and our red block, and they're oriented a little bit differently this time. And I'm going to look at these under 2 different situations. The first I'm going to consider is each block separate. So if we look at the green block's free body diagram, we have a normal from whatever that surface is on the green block. We have the green block's weight, and then we have a normal from the red block on the green block. Okay. All of these forces are caused by objects or caused by things that are external to the green block. If I now look at the red block, we have, again, a normal from the surface. We have the weight of the red block. We have the green block pushing back on it. And notice here we have 2 objects interacting, green and red. 2 forces that are in opposite direction. We've got the same type of interaction. We've got flipped subscripts. Those 2 are a third law force pair. And lastly, we have a normal force from that hand on the red block. And all of these forces are external to the red block. Okay. Now I'm going to re-envision this problem a little bit. I don't care how you think about it. Maybe you think that the green and the red are just a paint scheme and really it's one solid block of wood. Or maybe you think it's the kids who got into the super glue and glued them together, so it's essentially one solid block of wood. But regardless of how you want to view this, we're going to consider this as one object now. It's one block of wood. So whatever it is, it's a single block, which I'm going to label with a B for just being the block with its two paint colors. Okay, we got a normal from the surface on that block. We've got the weight from the earth on the block. And then we have a normal from the hand on the block. Okay. Well, it's the same system. So somehow we should be able to look at what we did on the left-hand side of the slide and look at what we did on the right-hand side of the slide and kind of look at them together. So you can see pieces. You can see, well, we just combine these two blocks. So this weight down here, for example, will be the red weight plus the green weight. I mean, it's one block now. Right. Okay. Well, same thing with these two. Those two normal forces must combine to give what the surface is doing to the combined block. But that leaves us with this guy, the hand. Well, over here, the hand was only touching the red block. Okay. So this one and that one are more or less equivalent. And so now the question becomes, what happened to our third law force pair? Okay. They came from the interaction of our two blocks. When we joined our two blocks into one, however you want to think about it, those forces moved from being external to the two blocks when they were separate to becoming internal to the two blocks when they're combined. So if you want to think about it, they're both on this free body diagram potentially. But because they are equal in magnitude and opposite in direction, they cancel each other out and you don't need to consider them or draw them. Okay. One last thing. You might be wondering how mathematically this all works out. Because if, as I argued, this force and that force, the ones that are circled in red, are equal, how do we get the same acceleration out? How do we get the green block to accelerate, for example? Okay, so let's pretend that this is a 5 Newton force. That makes this one over here that's circled a 5 Newton force. Okay, the red block will use a portion of that 5 Newton force to cause it to accelerate, and it will work out such that the piece it uses is enough to give it the proper acceleration. Now, how do we determine what piece it uses? Well, remember when we apply Newton's second law here, F net equals ma, we would take the normal from the red block, from the hand on the red block, and subtract off the normal from the green on the red block. And this is the chunk that gets taken away that isn't used by the red block. That last point may be a little bit confused. In either the second or the third section, I can't remember exactly where the example is. I do an example on a drone delivering a package, and I go through the math of how that works in that example. So, we've got Newton's 3 laws at this point. And the question is, can we put them all together and apply them to a single situation and see how that results in what we experience? So, for each of Newton's 3 laws, how do they apply to a person feeling pushed backward in their seat as an airplane accelerates down the runway? Okay. Third law, fairly easy. Normal from the seat on the passenger is equal and opposite to the normal from the passenger. Oh, goodness. Passenger on the seat. Okay. Second law, also fairly obvious. The net force on the passenger has to equal the mass of the passenger times the acceleration of the airplane, because the passenger is accelerating with the airplane, and it would be really bad if those weren't the same. If you think about it, the force on the passenger, which actually causes the passenger to accelerate, is the normal from the seat, because that's what they're in contact with. Okay? The first law is tricky. Okay? But it's all about this whole feeling pushed backward bit. Because remember what that passenger is going to want to do. Right? First law says that an object is going to want to stay at rest. Unless, or stay moving with constant velocity, which could be at rest, unless there's a net external force. So that passenger is trying to do exactly that. So you have a passenger sitting in the seat trying to stay at rest, and what happens as the plane begins to accelerate? Well, that pushes the seat back up into the passenger. So it feels like the passenger is getting pushed backward into their seat, because they're getting squished into the back as the seat moves into them, almost, if you think about it. Okay, that concludes this section on Newton's third law. In the next two sections of this unit, we are going to be working 4 examples that involve Newton's second law and, in some cases, Newton's third law.